As we continue into the information in chapter 8, just going to do one type of problem with this, but we're going to talk about finding a general solution to a homogeneous system of differential equations. So the derivative of x equals 1353x, right? And if we can solve it, when we can solve it, we get x equals c1 x1 plus c2 x2, because two equations, right? Which is c1 1 minus 1 e to the minus 2t plus c2 3 5 e to the minus 6t, because the solution vector is k e to the kt, k1 and k2, where k1, k2, the lambda 1 and lambda 2 are constants, which are we promote to ask whether we can find a solution. So if we have a general linear first order system, x prime equals a times x, where a is an n by n matrix. Okay? That's the coefficient matrix. Okay? Here's a 2 by 2 in this case. When we have that situation, we can try to solve the system. And we do it using what we call eigenvalues and eigenvectors. So here's the theory of it, and then we'll use it to do it. Okay. So if you have that nth order system of differential equations, okay, such that x prime equals k lambda e to the lambda t. So the system becomes, you go here, okay, x prime, right? X prime is k lambda e to the kt, which equals a k e to the lambda t, not kt, lambda t. After dividing out e to the lambda t, we get that ak is equal to lambda k, or ak minus lambda k equals 0. And since k is ik, the last equation becomes k. These said you can only subtract vectors. Okay, so you have to have the identity vector times a constant to have a vector there. So we factor out a k, and we got a minus lambda I k equals 0. So the matrix equation is equivalent to here, right? A11 lambda k1 plus A12 okay, k2 k21 k1 plus A2 minus lambda, because I is the identity matrix. 1 0 0 0 0, next term 0 1 0 0 0, next one 0 0 1 0, 1's down the diagonal. So that means that the subtraction, this guy is 0 except on the diagonal. So at 1 1, that's not 0. At 2 2, it's not 0. At 3 3, and so forth. Okay. Thus, to find a non-trivial solution to this differential equation, a non-trivial solution to this differential equation. To find that, okay, we must find a non-trivial vector k that satisfies, k is a vector, because these are all vectors, okay, that satisfies the conditions. In other words, we need to find a solution other than the obvious, which is k1, k0, and we must have the determinant of a minus lambda I equaling to 0. So that's what we have to have here, because this isn't 0. K1, K2, K3 isn't 0. Then this piece is the piece that has to be 0. And lambda is called the characteristic equation of the matrix A, and its solution are the eigenvalues of A. So a solution, K does not equal 0 to this problem, corresponds to an eigenvalue lambda, which is called the eigenvector of A. A solution to the homogeneous solution is then K, x equals K e to the lambda t. So we're only going to look at the one condition here. The others get a little bit edgier. But if we have lambda 1, 2, 3, and they're distinct real eigenvalues of the coefficient matrix A of the homogeneous solution, and K1, K2, K3 be the corresponding eigenvectors, then the general solution on the interval from minus infinity to plus infinity is given by x equals C1 K e K1 e to the lambda 1 t plus C2 K2 e to the lambda 2 t. So you have an interval. So let's see an example. Here is a linear system. dx dt equals 2x plus 3y. dy dt equals 2x plus y. So we're looking for x and we're looking for y. We're looking for two solutions. We're looking for two solutions. So we need to find the eigenvalues and the eigenvectors of the matrix coefficient. So we need to figure out this determinant. So the matrix A is 2, 3, 2, 1. So that's what A is. Eigen I is 1, 0, 0, 1. 2 by 2. So the determinant of this is going to be A minus lambda, 2 minus lambda, 3, and then 2, 1 minus lambda. So it's 2 minus lambda times 1 minus lambda, 2 times 3. So when we do this, we get 2 minus 3 lambda plus lambda squared minus 6. And 2 minus 6 is minus 4. So we have this, and if we can solve it, and the only ones we're really going to do in this chapter, in this ending sections, here is when they're distinct. So this factors to lambda plus 1, lambda minus 4. So lambda 1 is minus 1, lambda 2 is 4. So when lambda 1 is 1, or it's minus 1, then this guy up here becomes 2 minus a minus 1 is 3, and 3, and 2, 1 minus a minus 1, so we get 2. So the A ends up being 3k1 plus 3k2 equals 0. 2k1 plus 2k3 equals 0. k1 equals minus k2. That's what this tells me. So I can let k be anything. And so they decided to let k2 be minus 1. That means k1 is 1. So there's our k1. Lambda 2 was 4. So 2 minus 4 is minus 2. So we get minus 2k1 plus 3k2 equals 0. And 2, 1 minus 4 is minus 3. So 2k minus 3k equals 0. So both of those tell me that k is 3 halves, k1 is 3 halves k2. Again, we can use anything, but to avoid fractions, let's let k2 be 2. Then k1 is 3. I mean, I could let k2 be a billion, and then this would be 3 halves of a billion. Doesn't matter what you put here. Okay, those values will vary. Since the matrix is a 2 by 2, And since we have found two linearly independent solutions, then K1 solution is 1 minus 1 e to the minus t, and x2 is going to be, the second solution, is going to be 3, 2 e to the minus 4t. So the solution is C1 minus 1 minus 1 e to the minus t plus C2 3 halves e to the minus 4t. Now remember, C1 and C2 are just constants. So the constant times this, and with the constant we were giving initial values times this, would give us a number. That's why it doesn't matter what values you really use here, as long as you use them in the corresponding. I could let K be 4, K2 be 4, then K1 is 6. But that would change the C when we're doing it. So that is how we do these kinds of problems. So I'll do a pen cast on one, and you look at a couple of other examples, and I think it's not going to be that difficult.